So what is true about all polynomial functions? Well, all polynomial functions have what we call a continuous graph. Okay? What does this concept of continuity mean? What does it mean for a graph to be continuous versus not? But that goes on infinitely. Well, what if I have a graph that starts here and ends here? That graph is continuous. Doesn't have any breaks. I like that. That is my favorite. It's still an informal definition, but that's my favorite definition of continuous. You can draw the thing without ever having to lift up the pen.
There's no gaps or overlaps.
Right, well, it can't have overlaps because there wouldn't be a function. Right, so we're talking continuous functions. So you can't have overlaps, wouldn't be a function. Can't have gaps, you can't draw it without lifting up your pen. Right, that is the essence. So here's an example of a continuous graph. Here's an example of a graph that has a discontinuity. Now, is this graph continuous anywhere? Are there points where it actually is continuous? Yeah, like let's look at this point right here. Can I draw from the left of that point through it and to the right of it without lifting up my pen? Yeah. So there are lots and lots of points on this graph where the graph is continuous through that point. But there's clearly a point where the graph is not continuous. You cannot draw from the left of that point to the right without having to lift up your pen. Agreed. Okay. Informally, we call this a jump discontinuity. Okay. Very informal. Most of the time, those types of discontinuities are seen in graphs that are piecewise. Though, do all piecewise functions have discontinuities? No. Think about the graph that represented that cat falling from the plane to its death. That's a continuous graph, right? That cat starts off accelerating, and then all of a sudden hits terminal velocity, and then it goes linear, right? Part parabola, part linear, but you draw it without lifting up your pen. It doesn't instantaneously go from, 10 miles per hour to 20 without hitting all of the speeds in between. Okay? It is a continuous graph. So not all piecewise are discontinuous. Your two pieces can match up perfectly to where you draw them without lifting up your pen. But if I take this piece and shift it down a little bit, now there's a jump, discontinuity. What other types of discontinuities have you seen in the past? You remember? You should have seen some graphs in Algebra 2 that look like this. It's a graph that looks a whole lot like a polynomial, but there's actually a single point missing from the graph. Okay? Do you remember seeing anything like that? We would informally call this a hole. Okay, it's a discontinuity. There's a big difference between a jump and a hole when it comes to things like calculus. Okay? We call this a removable discontinuity because I can easily simplify, do some quick mathematics to come up with the equation that's the same, but actually goes through there. Where this is not removable. You can't easily create a graph that has that discontinuity removed. So that's a discontinuity. Now, what is the domain of this function? It would be all reals except whatever the x-coordinate of that hole's location is, right? There would be a number not in the domain. If this is at 5, then when I plug 5 into that function, its output is undefined. Okay? But what if I talked about this function here? First of all, is that still a function? Does it pass the vertical line test? Yes. If I plug 5 in, what is its output? Something, whatever the y coordinate of the black dot is. So what is the domain of this function? It's actually all reals. But is it continuous? No, it's still considered discontinuity. You have to lift up your pen to draw that. We call that a displaced point. Okay? It is also considered a removable discontinuity, just like a hole is a removable discontinuity. These all make sense? So polynomials are always continuous. If a graph is not continuous, Can it still be considered a polynomial? No. If a graph has discontinuity, it's automatically not a polynomial. It works both ways. If it's a polynomial, it is continuous. If it's not continuous, it's not a polynomial. Those are called contrapositive statements of each other. What's the other type of discontinuity you saw in Algebra 2? You probably are more familiar with this than any other type of discontinuity. What's that called? Yeah, you're doing it right. What's it called? The L thing. Asymptote. Vertical asymptotes. A vertical asymptote is a type of discontinuity. You cannot draw from the left of that vertical asymptote to the right without picking up your pen. Not a polynomial, clearly. Okay? So any type of discontinuity is not a polynomial. So let's do an example. How about y equals negative x squared plus 6x plus 1? Can you tell me, yes or no, is that a polynomial? Yes, I mean, we saw the definition of what a polynomial equation looks like. Something x to the something, plus something else x to the something else, plus something else x to the something else. That fits that pattern. That is a polynomial. So what can you tell me about its graph? It's everywhere continuous. You can draw the whole thing from negative infinity to infinity without ever lifting up your pen. Right? So it's definitely a polynomial. The graph is everywhere continuous. Now, what if I change this a little bit? What if I say f of x is negative x squared plus 6x plus 1 if the input is any number other than 2, but will output 172 if the output is 2. Is the graph of that continuous? No, it's at displaced point, right? The domain's still all reals, but it has a displaced point. So therefore, it's discontinuous. So is that function a polynomial function? No, it's not. Is it polynomial-like? Oh yeah, it's very polynomial. But there's this darn 2 where it is discontinuous. Okay? This concept is huge in calculus. What if I change this, though? What if I just wanted to be a pain in the butt? Is that graph continuous? Yeah. Why? Because what do you get when you plug 2 into negative x squared plus 6x plus 1? You get 9. So, yes, that's a continuous graph, and it is a polynomial, but that's a really stupid piecewise function, because what is that piecewise function actually the same as? Just saying that. So, I don't know. Maybe you want to be tricky. But luckily, you know I don't like trick questions. Okay. So, all polynomials are continuous. Are all continuous graphs polynomial? That's called the converse. No, there are lots of continuous graphs, everywhere continuous, that are not polynomials. Sine is one of them. Cosine is one of them. They are not polynomials. They are continuous everywhere. E to the x, right? Your exponentials. Those aren't polynomials, but they are continuous everywhere. Yeah. Well, here's a new concept. Not only are polynomials everywhere continuous, they are everywhere smooth. Whatever that means. Also a very calculus-y concept. In calculus, we don't call graphs smooth. We call them everywhere differentiable. That means everywhere the slope is nicely defined. It's probably the first time you've ever heard the word slope used on a graph that's not a line. The concept of slope does not only apply to lines. The concept of slope applies to all graphs. That's what calculus is all about. How do you find the slope of a parabola? How do you find the slope of that? Okay? A graph is considered smooth if every single point on the graph has a nice defined slope. Like this point right here has a negative slope. At this point right here, even steeper negative slope. At the very top of this hill, the slope is exactly 0. In fact, every single hill and dip at the very top Every maximum and minimum has a slope of 0 if the graph is smooth. Guess what the slope is at this sharp turn? Undefined. Sharp turns do not have defined slope. All of that will make more sense next year in calculus. All you got to realize is polynomials cannot have sharp turns. They cannot. You see a graph with a sharp turn, not a polynomial. And absolute values are not the only types of graphs that have sharp turns. In fact, here, I'll graph you one real quick. Well, I was going to. Here, how about this? Let's do the graph of square root, parentheses, x squared minus 4x minus 1 squared, like that. Let's see what that graph looks like. Whoa! 2 sharp turns. Is that a polynomial? No way! It's surprising word. I actually created one with sharp turns. Okay? Not a polynomial. 2 sharp turns. Not smooth. Okay, you can't quite tell. How do I know that that's a sharp turn and not just a really quick, smooth turn? It is a sharp turn, just trust me. Okay? Now, I kind of cheated. How did I kind of cheat? I square rooted a square, which is essentially the same as absolute value. Lots of radicals. Because of this concept of radicals and squares, lots of radicals actually have sharp turns. So there you go. Okay. So let's start graphing some. Let's start graphing some simple polynomials and get a feel for what all polynomial graphs look like. I'm going to use a piece of software here. I'm not going to call it my favorite mathematics software in the world because there's another piece of software that I've been using since I was in high school. It's called Mathematica. It is wonderful. But this is great because the big difference is this is free, open source software. It's written in Java. Maybe like take the AP Comp Sci here, you learn some Java. You can go on to the GeoGebra website, download the source code, make some changes to it, and make your own little custom GeoGebra. And if you add some cool changes, submit your code to the GeoGebra organization. If they like it, they will include it in their next version. It's pretty neat. And because it's Java, it works on Mac, Windows, Linux, and it's very cross-platform. I've had it working on Android, but it's hard on the small little touch screen. It will not work on iOS. But that's most things. Yeah. All right. So the reason it's called GeoGebra is because it combines geometry and algebra. Unlike there are other softwares like this, Geometry, Sketchpad, Cabri Geometry, but they're geometry only. GeoGebra is great. You got this input bar down here, so I can graph anything like y equals x to the second. Boom. Nice little parent parabola, yeah? And then I can use my geometry tools. I can do something like, let's make a circle. It has a center here and a radius of 2. Oh, and now that circle is stuck to my parabola. I don't know why I would do that. Pretty cool. Nice. Maybe put a point on the circle. Maybe draw a tangent to the circle at that point. Oh, wow. That's sweet. I mean, I don't know. There's really cool stuff you can do. But pretty powerful stuff. We actually use this in robotics quite a bit. It's a good way to prototype things, make sure things fit, stuff like that, do measurements. It's a pretty cool tool. And the nice thing is, like this circle tool, for example, I can be like, boom, boom, there's a circle, and then it gives me the actual equation of that circle I just made. Pretty cool, right? It's great for vectors. This is the best software I've ever seen for vectors. So I'll show you that more when we start doing vectors. But I can take this point, which is now attached to the parabola. No matter where I move my mouse, the point is stuck to the parabola. And so it's essentially like a trace on your calculator, right? So let me show some more. Let me round to 15 decimal places. Okay? So this is a parabola, which is a polynomial. Okay? Now, one of the big discussions we had in earlier classes was this connection between the function f of x equals x squared and its graph. Okay? First of all, what is the word zero? What does the word zero mean for a polynomial function? So that, where it crosses the x-axis. X squared plus 1 never crosses the x-axis, but it does have zeros. There's a connection between zeros and where a graph crosses the x-axis, but zeros and x-intercepts aren't actually synonymous.
What x is put in zero?
Yeah, it's a function, right? Get a little function machine. A zero is what number goes in and forces this function to output? 0. So what is one of the zeros for x squared plus 1? I. And what's the other one? Negative I. If I goes in, what's I squared? Negative 1 plus 1? 0. So I is the 0 of x squared plus 1. What is the connection between zeros, the numbers that make the function output 0, and x-intercepts? An x-intercept is always a 0. That is correct. Are zeros always x-intercepts? No. Why not? Some zeros are imaginary, and if they're not imaginary, they are what? So I guess the real statement is this. Are all real zeros x-intercepts? Yes. X-intercepts are your real zeros. Imaginary zeros you don't see in our graph at all. How many zeros does a polynomial function always have? It's always equal to its degree. So degree 5 polynomial will always have how many zeros? 5. What else is true about the imaginary zeros? They always come in pairs, right? Conjugates. And we'll be reviewing all of this week. Okay, today I want to focus on the graph, so we're going to be mostly talking real zeros, but I just want to kind of remind us of all this stuff. So can a degree 5 polynomial have 2 real zeros and the other 3 are imaginary? No. They have to come in pairs. Cannot have an odd number of imaginary zeros. Okay, so let's go back to this. This is x squared. How many x-intercepts do you see? You see 1. How many zeros does x squared have? 2. Whoa, what? Because x-intercepts are what types of zeros? Real. So if you see 1 x-intercept, that tells me this graph has 1 real zero, which means the other one would have to be what? Which is impossible. I would look at that and tell you, no, that graph clearly has 2 real zeros. One of them is what number? 0, and what's the other number? 0 again. Numbers can show up more than once as a 0 of a polynomial. Okay? What's a sign that a function might have repeated zeros when you look at its graph? Touches the x-axis and then bounces away. It doesn't cross straight through it. Okay? That's a sign of a repeated root. Well, I don't want to ruin your day, but let's graph y equals x to the 5th. There's the graph of y equals x to the 5th. How many times does that touch the x-axis? Well, let's zoom in. And then maybe let's stretch this out so we can see it a little better. Come on. Well, why aren't you stretching? There we go. I'm just stretching the graph vertically, just so we can see it. Why isn't that going? Come on, GeoGebra. Failing me. Anyway. How many times does this graph touch the x-axis? Once. Where at? 0, right? We can put a point on there and verify it. It looks like it gets really close to the x-axis in lots of spots, right? But it doesn't touch it anywhere except 0. Look at the y-coordinate of that point off to the left. Super, super close to 0, but it's not ever going to hit 0 until we hit right there. And then when we go to the right of it, it's above 0 again. Okay, let me turn snapping off. So there you can see really, really close to 0, but it is still above the x-axis. Just to the left, it is below the x-axis. So here's an example where this graph crosses through the x-axis. It doesn't touch it and bounce away. Okay, what is the degree of this polynomial? So how many zeros does this polynomial have? 5. How many of them are real? All 5. And guess what they all are? The number 0. I'm going to list all the zeros of this function for you. 0, 0, 0, 0, and 0. Again. It's a repeated root, but it didn't touch and bounce away. Because guess what? If the number of times the root is repeated is even, what's the graph going to look like? It's going to touch and bounce away. If the number of times a root is repeated is odd, it's going to flatten out like this one did, and then end up going through it. Okay? I almost think of it like this. The number of times a root is repeated is how many times it's trying to fake me out. Right? It's like this graph's coming along like it's going to cross the x-axis, and all of a sudden it starts turning like, type, no I'm not.
Students, please pardon this interruption for some announcements concerning several bus changes.
Who is that?
Bus change star number 26 is now bus 37. Bus 88 is now bus 39.
I don't think he has announced in caliber voice.
Is bus 50. Thank you.
Okay. So, what's the difference between x to the 5th, which looks like this, and I'm going to graph another one, y equals x to the, give me a large odd number. I heard 33. Okay? Let me zoom out a little bit. So there's the difference. How many zeros does x to the 33rd have? 33. They are all what type of number? Real. Not only are they all real, they are all actually the number what? 0. So you can see it gets really, really flat. Look how flat this looks. But is it ever actually perfectly flat? Does it touch the x-axis anywhere else except at 0? It's always rounded, always rounded. But the more number of times a 0 is repeated, the more flat it gets near that 0. Okay? Because it can't make up its mind. Am I going to cross the x-axis or not? Or am I or not? Or maybe, no, yeah, maybe, no, yeah. Changes its mind like 30 times before it's finally like, no, I don't think, I think I'm going to go on my way and keep going. Okay? A 0 that's repeated once just cuts right through it. Doesn't flatten off. Those are the easiest to identify. If the graph just rips right through the x-axis, it's a 0 of multiplicity 1. So what if I were to take x to the 5th and just shift it down like 2? Have a good one. If you want to start the homework is due Wednesday.
Well, Monday night.
Yeah.
My dad and I want to go to the robotics meeting on Wednesday.
Yes.
But